You walk through the heart of Victorian London, past Georgian townhouses and ornate public buildings, and something catches your eye. High above the roofline, integrated into the architectural fabric itself, you notice peculiar metal structures. Metal towers projecting from municipal buildings, elaborate conductor arrangements adorning public institutions, and complex rooftop configurations that have absolutely nothing to do with lightning protection. A historical plaque might mention Victorian architecture. A tour guide might call it decorative ironwork. But if you dig into municipal records, if you examine preserved technical documentation, if you trace the paper trail through municipal archives and Victorian engineering journals, an entirely different story emerges. One that has been buried beneath layers of forgotten infrastructure and redefined history for over a century, between approximately 1870 and 1920. Britain experimented with electrical infrastructure, systems that don't fit neatly into the conventional narrative of electricity's development. Not a mainstream story, but documented extensively in municipal records, in patent filings, in the correspondence of Victorian engineers, and quite literally still visible if you know where to look and what you're actually seeing. The official history presents a linear progression: Faraday's electromagnetic induction, Edison's light bulb, the Pearl Street Station in 1882, and then centralized power grids spreading outward to eventually supply every building in every city. A clean narrative, a comprehensible story. But the reality was messier, richer, and considerably more technically sophisticated than that simplified version allows. Britain, particularly England and Scotland, was experimenting with power generation and distribution approaches that were completely abandoned once centralized coal power generation became economically dominant. These weren't failed experiments in the sense that they didn't work. They worked quite well within their specific technical constraints. They were abandoned because economic circumstances changed, because better alternatives emerged, and because the infrastructure required for those alternatives was built over the evidence of what came before. The physical traces remain. Buried in the infrastructure of British cities are the architectural remnants of experimental power systems. Copper conductors installed in ways that make no practical sense for simple lightning protection. Ceramic insulators positioned with deliberate precision on rooftops across different buildings in the same district. Metal framework configurations that appear on hospitals, municipal buildings, and industrial structures with consistent geometric patterns. These are not coincidences or random aesthetic choices. They are the visible remnants of Victorian engineering ambition, and they're still there if you understand what you're looking at. Consider the case of the electricity systems documented in preserved municipal records from Manchester. Between 1875 and 1895, Manchester was simultaneously Britain's cotton manufacturing capital and a center of electrical experimentation. City council records from the period preserved in the Manchester Local Library archives. Reference installations described specifically as auxiliary power apparatus and supplementary electrical collection systems. The terminology is deliberate and technical. These were not primary power systems designed to replace steam generation. They were supplementary systems designed to augment existing infrastructure, particularly for applications where reliability and continuous supply were less critical than for industrial machinery. The architecture of these systems reveals sophisticated understanding of electrical principles. The rooftop structures weren't random. They appeared consistently above building interior spaces where vertical distribution infrastructure already existed. Above stairwells, above utility shafts, above locations where the building's internal infrastructure for conducting wires already resided. This correlation between rooftop structure placement and interior utility routing isn't coincidence. It's engineering logic. You place your collection apparatus where the distribution pathway already exists, where vertical conductors can descend through existing building spaces without requiring additional penetrations through structural elements. The ceramic insulators you see on preserved structures represent decades of Victorian materials, science. They're not crude. They're precisely manufactured, suggesting standardized production, implying commercial systems existing at sufficient scale to justify manufacturing standardization. When you compare insulators across different buildings in different British cities, the patterns match. The mounting geometries align, the spacing intervals correspond. This is not decorative variation, this is standardization of technical components. the kind of standardization that emerges when multiple installations are being made according to common specifications. The documentary evidence is more substantial than most people realize. The Electrical Review, Britain's primary technical journal for the period, published extensive coverage of experimental systems throughout the 1880s and 1890s. Patent records filed with the British Patent Office document dozens of inventors working on systems for collecting ambient electrical potential, for distributing power through copper conductor networks, for regulating voltage using various mechanical devices that were the precursors to modern electronic regulation. These patents weren't fringe documents. They were filed by engineers with serious credentials, backed by companies with substantial capital. Designed to address specific practical problems that Victorian Britain was attempting to solve, one particularly well-documented case involves the city of Birmingham. Preserved in the Birmingham Central Library are detailed municipal council minutes from 1887 through 1905 that specifically reference electrical installations and experimental systems. The terminology used in these official documents is precise: permanent atmospheric collection apparatus, supplementary direct current generation, indoor distribution systems with manual switching apparatus. These aren't vague references, they're technical descriptions entered into official records, suggesting systems formal enough to warrant municipal council discussion and decision-making. The economic context for these systems is absolutely critical to understanding why they existed and why they disappeared. In the 1870s and 1880s, electricity was not yet the dominant force it would become. Coal remained absolutely central to British industrial power. Steam engines, steam generators, and coal-fired furnaces powered virtually everything. If a building wanted electrical current, they had a limited number of options. They could install their own generator, driven by a steam engine, which was expensive, required fuel delivery, required skilled operators, and required substantial maintenance. They could potentially connect to an emerging local generating station if one was nearby, and if local legislation permitted it. Or they could experiment with alternative methods of generating or collecting electrical potential from natural sources. For many Victorian entrepreneurs and municipal administrators, the third option was attractive precisely because it required lower capital investment, because it didn't depend on fuel delivery supply chains, and because the technical knowledge wasn't yet standardized into a single dominant approach. Experimentation was economically rational. Multiple approaches coexisted because no single approach had yet achieved overwhelming economic superiority. This was an open technological frontier, and British engineers were genuinely exploring it. The rooftop structures themselves served multiple documented purposes, depending on their specific configuration and installation. Some were designed to exploit atmospheric electrical potential, capturing the naturally occurring potential difference between the Earth and the upper atmosphere. This isn't fringe science, it's documented physics. The atmospheric electric field is real, measurable, and has been carefully studied by meteorologists and physicists for over a century. In fair weather, the potential gradient is approximately 100 to 150 volts per meter of vertical altitude. On a 10-meter structure that represents roughly 1,000 volts of potential difference between the top and the ground, the challenge, as Victorian engineers understood perfectly well, is that voltage alone doesn't generate useful power. Power requires both voltage and current, and the current available from atmospheric collection is extremely limited because air is an excellent electrical insulator. However, with carefully designed electrode configurations, with proper grounding systems, with appropriate circuitry to store and regulate the collected charge, it was possible to generate small but genuinely useful amounts of electrical power under favorable atmospheric conditions. The patent records document this explicitly. Inventors specified modest power outputs measured in watts, acknowledged that collection was intermittent and weather-dependent, and designed systems that included battery storage to smooth out variations in supply. Other rooftop structures, particularly the more elaborate ones found on industrial buildings and municipal structures, appear to have been designed to capture earth currents. These are the natural electrical flows that exist within the Earth's crust, driven by geomagnetic activity, by mineral composition variations, by moisture distribution in soil, and by subsurface temperature gradients. Again, this is documented physics, not speculation. Geophysicists today measure earth currents continuously for research purposes. Victorian engineers recognized that appropriately positioned electrodes could tap into these currents and extract measurable electrical potential. The technical sophistication becomes evident when you examine the specific implementations. You don't just stick a metal rod in the ground and expect to get electricity. You need carefully designed electrode configurations, optimized for the specific geological conditions of the installation site. You need multiple electrodes positioned at optimal depths and separations. You need understanding of soil chemistry, of how different soil compositions affect conductivity, of how moisture variations seasonally affect performance. The preserved diaries and notebooks of Victorian electrical engineers document exactly this kind of systematic experimentation, testing different electrode materials, different depths, different spacing configurations, measuring the resulting electrical potential under varying conditions. Consider the preserved records of the Leicester Institution, an organization dedicated to scientific investigation that operated throughout the Victorian period. Their archives, maintained by the University of Leicester, contained correspondence between electrical experimenters, detailed notes on attempted installations, measurements of electrical potential under various conditions, and discussions of the practical challenges encountered when trying to implement these systems at any meaningful scale. The engineers weren't naive. They understood the fundamental physical limitations. They were attempting to optimize within those limitations, seeking ways to extract maximum useful power from ambient environmental sources. What makes this historical period particularly fascinating is that Britain was simultaneously pursuing multiple electrical infrastructure pathways, while some engineers and industrialists were experimenting with rooftop collection apparatus and earth current extraction. Both approaches were being pursued. The patent records show active parallel development. Municipal records show installations of both types. This wasn't a case where one approach was suppressed by authorities in favor of another. Rather, it was a case of market selection, where the trajectory of technological development and economic evolution gradually made certain approaches obsolete. The transition was gradual, but ultimately decisive. By the 1890s, particularly after the Electric Lighting Act of 1882, and subsequent legislation that clarified the legal framework for commercial electricity distribution, centralized power stations began to proliferate across British cities. The economic calculation changed. If you could reliably connect to a municipal power grid, the advantages became overwhelming. No need to maintain rooftop collection apparatus. No need to worry about atmospheric conditions or seasonal variations. No need to maintain battery storage systems. Simply pay a monthly bill and receive reliable power on demand. The temptation to abandon experimental systems in favor of grid connection was economically irresistible. The physical removal of these systems followed logically. The valuable components, copper conductors particularly, had salvage value. The ceramic insulators and metal framework gradually disappeared as buildings were renovated, upgraded, or repurposed. But the mounting holes remained, the electrical penetrations through roofs remained, the architectural scars remained, the evidence persisted, while the knowledge of what those structures actually were faded into obscurity. This knowledge disappearance wasn't through deliberate suppression, but through the ordinary process of technological succession. When electrical engineering became formalized as an academic discipline in universities, the curriculum naturally centered on what was currently relevant to practice: centralized power generation, long-distance transmission, municipal distribution networks. These were the technologies that mattered professionally: rooftop collection apparatus, atmospheric electricity capture, earth current extraction. These became footnotes, historical curiosities, artifacts of an earlier experimental phase that had been superseded. The textbooks changed. New generations of engineers never learned what previous generations had routinely implemented. Technical journals gradually stopped publishing on these topics because nobody was actively researching them anymore. The last practitioners, the engineers who had maintained these systems and understood their operation, retired or died. Their tacit knowledge, their practical understanding of optimization techniques, their experience with geological variations and soil conditions, all of this accumulated expertise simply evaporated from the collective knowledge base. What's particularly instructive about this historical case is what it reveals about how technological knowledge is preserved or lost. A complete patent record exists. The blueprints and technical specifications are preserved in governmental archives. Publications exist in Victorian technical journals. Yet, despite all this documentation, the practical knowledge of how to actually build these systems, how to optimize them for different conditions, how to maintain them effectively, has effectively disappeared. You could read every preserved document and still not possess the tacit, experiential knowledge that a Victorian electrical engineer working with these systems for several years would have internalized through practice. The buildings themselves preserve traces. If you walk through central London, through Manchester, through Edinburgh, through any major British city that industrialized during the Victorian period, you can see the evidence. The metal framework on municipal buildings that served no purpose as mere lightning protection, the ceramic insulators on preserved rooftops mounted with deliberate precision, the electrical penetrations through roof structures, now sealed but architecturally visible, the copper conductor paths marked by oxidation staining on brick and mortar. These are the archaeological remains of an alternative technological pathway that was chosen but ultimately not pursued. What this history reveals is something profound about technological development itself. We tend to imagine progress as inevitable, as the superior technology naturally triumphing over inferior alternatives through the inherent logic of efficiency and capability. But what actually happens is far more complex. Technologies emerge that work, that solve real problems, that deliver genuine benefits within their specific context. Then economic and infrastructural circumstances change. A superior alternative becomes available that is better suited to the new circumstances. The older technology becomes obsolete, not because it fails, but because context has shifted. The knowledge erodes not through conspiracy, but through the ordinary process of specialization and the natural human tendency to focus on what is currently relevant. The British case offers particular lessons because it happened at a specific historical moment when electricity was still genuinely undetermined, when multiple approaches were actively being pursued, when the outcome wasn't yet predetermined. By the early 20th century, the outcome had become clear. Centralized power generation powered by coal would dominate. Rooftop collection apparatus would become relics. The knowledge would fade. The infrastructure would be slowly dismantled. The historical record would be simplified into a narrative of linear progress. And British cities would preserve in their architecture the physical evidence of alternatives that nobody remembers. Today, if you know what to look for, if you understand the technical logic behind these installations, if you examine both the preserved structures and the historical documentation, you can reconstruct what occurred. You can understand that Victorian engineers were more sophisticated, more experimental, and more creative than the simplified historical narrative acknowledges. You can recognize that technological pathways are not predetermined, that alternatives genuinely existed, and that the outcome we inherited was selected through economic and practical forces, not through the inevitable superiority of the dominant solution. The towers are still there. The insulators remain. The metal frameworks stand on top of buildings that have served entirely different purposes for decades. They've been reclassified as decoration, as historical artifacts, as curiosities of architectural fashion.